Okay, so we've done number 1, and we created the confidence interval for the average age that babies become potty trained. And now we're on number 2, and we need to explain what 95% confidence means in context. Now remember, you don't have to do any of number 1 in order to do number 2 and get full credit. Number 2, explaining what it means. If we were to take several random samples of 15 ages of babies becoming potty trained, %95 of the confidence intervals we would make would contain the true average age that babies become potty trained. Now, this is crucial. A lot of people still on the quiz from the 8A didn't get the bonus correct. Well, I've only looked at 3, I can't say a lot. In several random samples of 15 ages of babies becoming potty trained, 95% of the confidence intervals, each of those samples, each one's going to produce a different confidence interval. Some of them will contain the true average and some will not. In fact, 95 out of 100 should contain the true average age that babies become potty trained, and 5 out of the 100 would not. Technically, that's what confidence means. So, it's a very hard concept to grasp. Sometimes you just got to repeat it over and over and over to yourself, and at some point the light bulb might go off. It might not be this month, it might be next month, or hey, it might be the beginning of May, right before the AP exam, until it actually sinks in. But the more you repeat it to yourself and try to explain it to yourself, the more it'll sink in. All right. Number 3, if we wish to conduct another trial, how many babies must we test? How many babies? We're looking for N. Must we test to be 99% sure of estimating the mean potty training age to within 2 months? Well, we have a problem here because our margin of error formula, remember this is, here's our normal curve, and we have X bar in the middle right now, and we're trying to come up with this interval, and we only want it within 2 months. Right now, our average age was 30.8, and if we want it within 2 months, that means we're going to go down 2 months, so we're at 28.8, and up 2 months, so we're at 32.8. And we want this to be a 99% confidence interval. We want to know the size N that we need in order to get that. Lots of ways you could tackle this. If you look at the formula, X bar plus or minus T star times your standard deviation over the square root of N. We have one slight problem. This right here is our margin of error. But we don't have T star anymore. We don't have T star because we need to look up to find our sample size. And when we look at our table, which back on number 1, I forgot to add this part to it. If we look at number 1, to get T star, here we go. To get T star, you need degrees of freedom. And for one sample mean, degrees of freedom is N minus 1. So I'm going to back up here to number 1 because we forgot to include our T star. degrees of freedom equals 15 minus 1, which is 14. And we did back up here a 95% confidence interval. So if I look up T star, got my table, on the bottom end at 95, my degrees of freedom is 15 minus 1 or 14. So I'm going to go up, 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 and over until I get to 2.145. Now I need to write that on my paper back up here on number 1 to ensure that I get full credit for the do part on there, because they're probably going to look for it. They may not, but they probably would. All right, here's the problem though, back down here at number 2. We don't know T star. There's no way we can find it because we don't know our sample size, so we can't figure out the degrees of freedom. So instead of T star, we're just going to use Z star. Not a big deal. We want all of this part, I boxed in purple, to equal 2 months. And the standard deviation, we're going to use the one we had before, which was 5.116 divided by square root of n. Now plugging in Z star for 99%, it's 2.576. So I have 2 equals 2.576 times 5.116, all divided by the square root of n. If I cross multiply, square both sides, I should end up with n equaling 43.488, which of course for sample sizes we should always round up. So n is approximately 44 babies with potty training ages. To test. Now, did it need to be written in context? I have no idea. If you're unsure, write out a nice little sentence about it so you ensure that you get the E for essentially correct and not the P for partial. All right, let's flip our paper over at this point. We're going to talk some more about confidence intervals with sample means. Number 4, we have the distribution of the number of vacation days per year offered by the different U.S. companies is skewed to the right. Okay, so this is saying your population is not normal. Remember our central limit theorem with our penny graph? The population was skewed. So it's skewed to the right. The average number of vacation days per year by different companies across the United States is 22 days. So across the United States, that's our mu, is 22. We collect data on the number of vacation days from a random sample of 60 companies in the state of Maryland. Why is it okay to use these data for inference even though the population is skewed? Well, according, I'm probably going to run out of room here, according to the central limit theorem, or CLT, we have a random sample. We have a random sample of 60 companies, which is greater than 30. And plotting the average of every sample of 60 companies will produce a graph that approximately normal. So remember the pennies? Our original population was when we just took the ages of all the pennies, you guys listed them in groups of 50, and the original population was very skewed to the right. But then when we took a simple random sample of size 5, it got a little more symmetric because we just plotted averages. So when n equaled 5, it was kind of a little more symmetric. It was still spread out. When n equaled 10, it got a little more symmetric. And then when n equaled 20, I remember Danny Kurtner said that's not possible. That's not, it can't be right. It looks false. Said something like that. Somebody else was sitting up front with him. They both agreed there's no way it was possible. But it was very symmetric looking because we just plotted the averages. It's the sampling distribution of sample means. All right, so next part. The sample of 60 randomly chosen companies produced a 95% confidence interval for the average number of vacation days of. Here's our interval. Does this interval produce evidence that companies in Maryland allow for fewer vacation days than the rest of the country? Well, wait a sec. What was Maryland? Way back up here. This is Maryland. The rest of the United States, mu was 22. Where does mu fall? Where was 22 fall between 23.7 and 32.72? It's below it. So what does that mean? If the average number of vacation days for the United States is 22, and Maryland ranges from 23.7 to 32.72, means Maryland has more vacation days on average. So 22 days falls below the interval of 23.7 to 32.72. So Maryland is actually providing more vacation days on average. Explain what 95% confidence means in this context. You can flip it over if you need to, but at some point you need to memorize this. In several random samples of 60 companies, (95% of the confidence intervals produced will contain the true average vacation days for Maryland. So we don't know what the true average is. I'm sure we could figure it out through a database somehow. But in this first sample up here, this is the one interval they came up with. If you took several samples, like 100 samples, 95% of those samples will have a confidence interval that contains the true average number of vacation days. 5 of the 100 would not. And that's what we're saying. Number 5, yay, multiple choice. We like multiple choice sometimes. Which of the following is true about students' T models? What's a T model? That's the T distribution that we were just using. And they are unimodal, symmetric, and bell-shaped. Well, if you're not sure, let's look back at our actual T table. Is it unimodal, symmetric, and bell-shaped? Yeah, it is. So that's true. They have larger variance than the normal model. What's variance? Variance is another word for spread. It's your standard deviation squared. Well, if you look at all these values in here, when we got down to infinity, we called that z star going across for the normal model. When the sample size was smaller, let's say sample size was 10, degrees of freedom is 9, you go over your standard error, or your t-star, excuse me, for 95 would be 2.262 compared to 1.96. So the spread is bigger. You're going more standard errors away in either direction. So yes, the spread is increased. As the degree of freedom increases, the t models look more and more like the normal. Yep. Because as your degrees of freedom increases, your sample size is increasing. As we get closer and closer to z-scores down here, we get closer and closer to z. So that's checked. That one works too. So all 1, 2, and 3 are true. A researcher found that 98% confidence interval for the mean hours per week spent studying by college students was between 13 and 17. Okay, which is true. Now they're just talking about the definitions. There's a 98% chance that the mean hours per week spent studying college students is between 13 and 17. Nope. Chance means probability. Confidence is not the same as probability because we don't know the true parameter. This is only based on one sample. So chance is a bad word when you talk about confidence. 98% of college students study. Nope, this is saying all. 98% of all college students studied between this one interval. No, that one interval is only based on one sample. So this is only for that one sample. It's not true for the whole population. So not 1, not 2. Students averaged between 13 and 17 hours per week studying on 98% of the weeks. No, that does not. This is only on one sample, so only for that one sample. So none of them. And then number 7, this is just plug in, plug and chug, see which ones work. We have a random sample of 15. So remember your t-star. That's what all these numbers right here are. Sample of 15. Your degrees of freedom should be 15 minus 1, so it's 14. They want a 99% confidence interval, so do yourself a favor and look up degrees of freedom 14, 99, and find that t-star. You will quickly be able to eliminate some choices. It's 2.977. So we're looking for 2.977. Well, yeah, I just eliminated C, A, and D. Now it's between these two. What's the difference? One is over your N, and the other one's over your degrees of freedom. So let's utilize our formula packet once again. It's supposed to be times your standard error. Let's look. Confidence interval is your critical value times the standard deviation of your statistic. Well, here for sample mean, it's sigma over the square root of n. At no point do you put it over the square root of your degrees of freedom. So, has to be B. Check. All right, so that's the rest of the practice for section 8.3. Hopefully that helped you out, and we'll see you. Maybe I get some, if I have some time, I'll put some homework problems up too. All right, thank you.